All right, so in this section we're going to talk about dipoles, and that's a new word for you, but basically we're looking at distribution of electrons across a bond. So when we have a molecule like HF, hydrogen monofluoride is one way we could name this, we talk about electrons being shared between these two atoms, between hydrogen and fluorine. This little bond in between is electrons, two electrons being shared, but the problem is we know that atoms have electronegativity values which describe their pull on shared electrons, which means shared electrons are not shared equally. Okay, so we have these differences in electronegativity. And as we can see here on this chart, 3.98 is the electronegativity value for fluorine. Hydrogen's is much lower at 2.20. So when we look at a covalent bond, we always have to think about the fact that, yes, we're calling it sharing, but it's not going to necessarily be equal sharing. And it results in a couple different kinds of bonds. So a covalent bond is not always just a covalent bond. So if the difference in electronegativity between the two atoms is greater than 0.4, that's going to result in what we call a polar covalent bond. So it simply means the electron is being pulled more towards one atom, in this case the fluorine, which has a much higher electronegativity, and away from the hydrogen end of the bond. And so polar just basically means that something has opposite ends, like a magnet, or the Earth has, a North Pole and a South Pole. Polar just means that there's a disparity, a difference between the two opposite sides. If there's not a big difference, so if you have two atoms that are pretty close together in electronegativity, or if it's just two of the same atom, like two oxygen atoms bonded together, that's going to be referred to as a nonpolar covalent bond. Because if it's a nonpolar covalent bond, those electrons are being shared roughly equally and therefore spending a pretty equal amount of time between the two atoms. Okay, so when we have a polar covalent bond, it's going to result in something called a dipole. And a dipole is just this little arrow symbol that you see over here with a little plus sign tail on it. So what we really see here with this table is that it's really just a continuum. We talk about ionic being a metal nonmetal and covalent being two nonmetals, but really there's a little bit more nuance to it than that, because it's really a sliding scale, and there's lots of shades of gray, I guess I should say. So if two atoms are more or less identical in electronegativity, then they're going to be a very nonpolar covalent bond. That's way down here at this end of the spectrum. As the electronegativity difference grows, though, the bond becomes polar, and eventually at a threshold of a difference of about 1.7, then it becomes an ionic bond. So in reality, it's not just as cut and dry as saying that it's metal nonmetal makes something ionic. It's really a big difference in electronegativity makes a bond ionic, but that almost always is because one of the elements is a metal and the other one is a nonmetal. Because if you put two nonmetals together, chances are the difference in electronegativity is going to be at most 1.5, 1.6. But it's probably not going to get into that 1.7 part of the scale and therefore be called ionic. Okay, so if we do have a bond that is polar, it creates what's called a dipole. And a dipole is just a way of describing the distribution of electrons across a bond. So if we go back to our example of hydrogen monofluoride, we already discussed that the electronegativities on these guys are very different. Hydrogen is 2.20, fluorine is almost 4. And so what that means is I'm going to be able to say that the electrons that are being shared there between hydrogen and fluorine are actually being pulled much more towards fluorine. And so it allows me to draw an arrow parallel to the bond. Doesn't matter whether I draw it above or below. I drew it below, but it's parallel to the bond, and it's pointing in the direction of greater electronegativity. That's the direction the electrons are going to be pulled in that bond. And then the tail of the arrow has a little slash through it, which makes it kind of look like a plus sign, which makes sense because if the electrons get pulled away from hydrogen, that makes the hydrogen end of the molecule like partially positive. Not completely positive. It hasn't lost its electron, but it's not getting a very good share of the shared electrons. Okay, so that is an example of drawing a dipole, which can be drawn for every bond. Anywhere that there's an electronegativity difference, we can draw a dipole. So if you have a bond that has multiple dipoles, so if it's a molecule, excuse me, that has multiple dipoles, that just means it's a molecule that has more than two atoms. So those can either add up or they can cancel out. So what do I mean by that? Well, water is a great example, H2O. So if you look at your electronegativity values in your notes, you can see that oxygen has a pretty high electronegativity, pretty high pull on shared electrons. Hydrogen, we've already seen, has a pretty low value of 2.20. So which way is the dipole going to be going for this bond here on the left? It would be going towards the oxygen end. So you see I've drawn it parallel to the bond, kind of off to the side, but it's going in the oxygen, in the direction of oxygen, because that's more negative, has a higher electronegativity. And then there's the same bond exists on the other side, so we should draw a dipole for that as well. Now, in this case, we're going to take a look at these two dipoles and see if they add up or cancel out. Okay. Well, if I have a force, going up and to the right, and then one going up and to the left, that left-right component gets kind of canceled out, right? And they're simply both going up. Another way of looking at it is if I travel, let's say, a block northeast, and then I travel a block northwest, where am I from where I started? Well, I'm north of where I started, right? So what do these two dipoles have in common? They're both going up. So I can draw what we call an overall or molecular dipole for this molecule, which is just in the general direction of oxygen away from hydrogen. So this dipole is my molecular dipole. That's why I circled it. It is the sum of these two individual bond dipoles. All right. And then if we have another example here, carbon dioxide, we've seen this one before. Carbon has an electronegativity of 2.55. And then we've already seen oxygen is 3.44. But because this is a linear molecule, and because both dipoles would be going out towards oxygen, those two dipoles are directly opposing each other. So it's kind of like a tug of war with equal, with identical twins on each side of the rope. You're pulling with the same strength in exact opposite directions, so the rope doesn't move. There's no left or right shift of electrons. They're just kind of canceling each other out. So anytime you have these dipoles pointing in the exact opposite direction, whether it's away from the center or towards the center, if they're pointing in opposite directions, in this case you could say east and west, they cancel each other. Because if you walk a block east and then you turn around and you walk a block west, well, you're right back where you started, so you really haven't changed your position. So what we would say for this one is they have canceled, and so therefore there is no net dipole, or you could say this is a non-polar molecule. Okay, go ahead and give these a shot. Draw the Lewis structure for each one. Add all dipoles that exist. So anytime you have differing electronegativities, you should be able to draw a dipole along every single bond. Unless they're identical atoms, they should have some difference in electronegativity. So draw all the bond dipoles and then see if you can figure out whether they add up or cancel out, and give you a net molecular dipole, or you would just say non-polar or no net molecular dipole if they do cancel. So go ahead and give those a shot, and we will go over those next time.